So tonight, we're pleased to welcome Chris Jagodzinski back to Mass Bay RE with tonight's program, Pennsylvania Railroad Electrification, the Keystone of High Speed. Chris's roots with Mass Bay RE go back to the 1990s when he worked on the Amtrak charters that were the backbone of our excursion program at that time. He's currently Assistant Vice President Operations for Amtrak, responsible for overseeing Amtrak train operations system-wide. He's been with Amtrak for 34 years, mostly in the transportation department, with some additional experience working in both the mechanical and engineering departments. Chris has been heavily involved in the testing, preparation, and launch of the next generation of Acela trains, which we hope to see on the rails before too long. Chris's program tonight will give us some historical background of today's electrified Northeast corridor, from the development of electric traction on the Pennsylvania Railroad, with some references to the New Haven, through the Metroliners, legacy Acela, and then the new Acela, along with some technical details about Catenary. So, Chris, welcome back to Mass Bay RE.
Well, thank you once again for the invitation. I really appreciate it. Like you said, goes back to 1990, probably 1989 or 1990 with the groups, and you guys have a great group. It's always a pleasure to be here. So thank you so much. I always enjoy talking to good groups like this. So thank you. And excellent presentation. Excellent. If folks, you haven't signed up for Mass Bay, you should do it. It's worth it. It's a good group. So I'm going to share my screen here. So just let me know when everybody can see it. And are we good to go, Dave?
Yep, looks good.
Okay, so thank you. So here to talk about, as we call it, the Pennsylvania Railroad Electrification, the Keystone of High Speed. So we'll talk about some stuff tonight where, we start with, what did the PRR do? Why did they do it? And I'm going to bring it up to how the Pennsylvania Railroad Electrification is really, the cornerstone of what laid, the groundwork for the modern Northeast corridors we know it, and then even the higher speeds that we're operating today, and even some higher speeds for the future. But so everybody here that's on here really knows a lot about railroads, trains, and things like that. But one thing that a lot of people don't understand is about electrification. And what I call electrification is really, I call it the fourth dimension of railroading. Okay, tracks, trains, equipment, everybody knows about that. But electrification really just as a whole nother way you need to think about it, how we need to manage it, whether you're fixing it, running it, operating it. It's a whole nother dimension outside of what a lot of people really think about. They don't have it out west. They don't have it down south. It's really a Northeast phenomenon with a few other, exceptions here or there. But, but there's really a lot to learn. Okay. So the PRR, there's a number of other railroads that did have electrifications around, but we're going to focus on the PRR today. And so one of the things I want to talk about is really, why did they do it? All right. Why did they do it? And really, the first thing, one of the biggest challenges that PRR had was back in around 1871 or so. They took over some railroads in New Jersey, and they got to here. What you see pictured is the Exchange Place Terminal, in Jersey City. They're a big competitor to New York Central. They got into Manhattan. New York Central had a route into Manhattan. Grand Central Terminal, came down there. The PRR was stuck at the water's edge here, and they were a huge corporation. They were a very proud corporation, and they just thought it was just it was just not good customer service to be able to put the people onto a ferry, take a ferry across what back then was a very crowded river, subject to fog and weather and just more delays, and then you would land sort of in Manhattan and just this on the Hudson River banks with just this chaos between taxis and trucks and just everything else that were going around there. Back in the day, the PR said, we need a much better entrance. If we're going to be the standard railroad of the world, as they saw themselves, we need a much better entrance to be able to get into Manhattan and to, make this majestic entrance they really wanted to make. So they're trying to figure out how to do it. There were some tunnels around, and there's tunnels out in the mountains and things like that. Can you tunnel on the river? Well, all they had at the time was the steam technology, and it's like, we can't do it. The steam, you would gas all the people out. You just can't run a steam engine under the river like that into Manhattan. The smoke, it would just be it really would not work. And plus the grades you would need, the steam engines would have a lot of trouble on the grades, through the tunnels underneath the river. one of the other proposals that was floated was to build a bridge over the Hudson River further upstream, from where Jersey City was, up around Weehawken or a little further up in Manhattan there. Because of the Hudson River is such an important artery of commerce in the New York area, in the New Jersey area. And for not only that, for national defense with the War Department, there were certain restrictions that was placed on you. You just couldn't put, nobody's going to put a movable bridge in the river. It was so important. It would always be opening. It really had to go up very high and then come down into Manhattan, to steer clear of the boats. It was part of the War Department's requirement. And really, they were looking at it. They worked with Gustav Lindenthal, who is a very well-known bridge designer, from back in the day, back in the 1800s. And really, it was such a huge project to take on. It was just this, as they say these days, ginormous, right? This ginormous project they would have to take on to get all these tracks and these trains there and to build a terminal, and then the trains would have to loop around to get back down to sea level because the bridge would come in so high. And one of the other things then too was, what really also was a challenge for the bridge was the fact that, all these steam engines had to be serviced somewhere. They're in the city, you're going to drive down property values, the congestion in the city. They couldn't find a way to make it work. Plus the finances on it. At the same time, they try to get the other railroads to go into it. So what is the PRR, the CNJ, the Erie, it's the Erie and the Lackawanna, separate railroads, back in the day. Do they all want to go in on it together? And none of the other railroads really felt they had the cash or the finances to be able to go finance such a bridge and then to go try to compete with the PRR on the bridge or or share it and just everything. It was just a match. So it never really happened. Okay. So it never really happened just because of all those other reasons here. But ultimately, though, they figured out a situation in terms of what they could do here. Okay. They figured out what they were going to do. And, one of the things that was happening at the time by the late 1800s, all right, there was a couple things that were happening with railroad electrification. 1895, the B&O Howard Street Tunnel in Baltimore is really the first mainline electrification for steam railroads. When the B&O had to build their, extension up to, Philadelphia, back in the 1800s, they had to get through downtown Baltimore. They couldn't do the street running in Baltimore. They built this thing called the Baltimore Beltline, but they had this several-mile tunnel underneath Howard Street with a grade, and it was just going to be atrocious for steam engines to operate through. And the B&O in 1895, one of the first mainline electrifications with DC power electric locomotives, were able to couple these electric locomotives up, haul the freight train up the grade through the Howard Street Tunnel, cut off, on the other side and go on their way. Also around the same time, right around the turn of the century, Samuel Ray, some folks know him who know the PR history. He was a vice president of PR at the time, was over in Paris. And at the Gare d'Orsay, had just opened in Paris. So it was a short underground railway tunnel underneath the Seine River where the trains could come in powered by electricity, could come into the station under the river to an underground terminal on the bank of the Seine. And Ray Solenson says, this works. This can work. This can actually work. I see a vision for Penn Station now. He was working for the president of the PRR at the time, A.J. Cassatt, and he convinced Cassatt to go over and see it. And at that point in time, they decided we can do Penn Station. We can do this. We can dig, make the tunnels, and we'll talk a little bit about what that is in just a few minutes here, because they saw what the electrification can do. So in 1901, actually, A.J. Cassatt came out and announced a plan for Penn Station. Actually, the decision happened a little bit before that, because one of the things that the PRR did wisely was if they had, put word out earlier that, hey, we're going to build the station, here's where it is, everybody was going to jack up all the property prices. So what the PR was able to do is through a shadow organization, if you will, they went out and they started buying up all these different properties in the Tenderloin district, between 31st Street and 33rd Street and, all this property in Manhattan. They started buying it up. And, because that's where the future Penn Station was going to go. So publicly in 1901 is finally, when they announced it. One other thing that did take place also in January 8th of 1902, there was a collision in the Park Avenue Tunnel. So many folks that are on here probably know that the New Haven and New York Central, shared right away down into Grand Central. And there was a collision between I think it was a Danbury train from the New Haven, and I forget where the New York Central train was coming from. But because there was a tunnel with the steam engines that had to go through this tunnel underneath Park Avenue, the engineer missed a signal. No PTC back in the day. That's we haven't done the PTC talk here, have we, Dave? We'll have to do that one of these days too. We can talk about that in the future. So anyway, the two trains collided. Everybody in New York was very upset about it, and they passed a law. The New York City passed a law that said basically, in effective January 1st of 1908, all steam locomotives would be banned south of the Hudson River. So at this point in time, we also knew electrification was coming. This really is actually after they already had made the decision to get it there, but this just only cemented it. That says, we're going to do it. All right. So what do they actually do? So we can see the map, and hopefully, Dave, you can see my cursor here. Was this showing up on the screen?
Sure can.
Okay. All right. Very good. So here's where the Jersey City terminal was, right over here. It's across from Lower Manhattan, right? The original main line went this way, through the meadows, came out through Harrison, New Jersey, Newark, as folks know, and off you go, down to Elizabeth and Trenton and other places like that. So this is where the original Jersey City terminal was. So what they decided to do is we're going to build this new place uptown here called Penn State, right here, PRR terminal, Penn Station. All right. So Penn Station would come out here underneath the river, make a left after you came through the Bergen Hills, cut across the Jersey Meadows, down through Harrison once again, and come out this way to go to Newark, and then once again. So the PRR terminal here. And one of the things that's interesting actually is because you see where the terminal is here, and up here, it's a further distance to travel. It's actually 1.4 miles longer now to New York City. And to this day, if you're riding a train between Newark and Philadelphia, for the folks who look out the window and see the milepost there, those mileposts are actually measured from Jersey City, believe it or not. The 0 milepost is right there at the bank of the Hudson River for the Northeast Corridor. All right. And to this day, it's funny, when you leave Penn Station, there's actually another milepost 0 at Penn Station, but you go here, you go to 8.4 miles before you get to Harrison, or it's the location of the old Manhattan Transfer, where the two lines join up, and you go from 8.4, and all of a sudden it starts over again right at 7.2, and you keep, so you keep going. So it's roughly about the 90 miles, but there's actually two sets of duplicate mileposts in here because when they extended it, it's actually a little bit longer. One other interesting thing here too is when the PR conceived of Penn Station, all right, when the PR conceived of Penn Station, all the long distance, they really wanted the big entrance to be for the lucrative long distance trains. All right. And they really didn't have a good plan yet to how to deal with the short haul commuters, which was really starting to be a growing business here by the turn of the century. So what some folks don't know, my cursor keeps disappearing here. So hopefully, I don't know what's happening to it here. Originally, the plan was to run the electrification out to here, right to the Jersey Meadows where the bend is. And right there is where they would cut off I guess that's in the Bergen Hill right here. They would cut off the electric engine here, put the steam engine on, and then it would go the rest of the way. But the PRR really did not have a good plan to handle some of the other commuter trains in here. This is more of a long distance thing going on. So they actually worked on a joint deal with the Hudson and Manhattan Railroad, which was still in 1908 or so, boring their tunnel, underneath the Hudson River to go over towards the World Trade Center and up to 34th Street eventually. They actually worked on a deal where the PRR and the Hudson Manhattan went on together and actually jointly operated lines. So they're sort of turning this into a rapid transit line, and the engine terminal was moved from this location here at the Bergen Hills and was moved down to Harrison, New Jersey, at the place which would eventually become known as Manhattan Transfer. All right, Manhattan Transfer, the yard is still there. It's called Hudson Yard. One of the towers, Hudson Tower, you can still see it by the PATH trains for the folks. If you just between Harrison and, before you cross underneath the Jersey Turnpike tunnel there, you can actually still see it. But the transfer was moved out to here, and that way some of the local people who still had to go to the financial district in Lower Manhattan actually had an option to go this way, change to a PATH train or to a Hudson and Manhattan train. Take it to Lower Manhattan. You could ride the train up here, or even some of the rush hour trains, stayed. Even when Penn Station was open, some of the rush hour trains would actually still go here for those bankers and the financial folks coming up from New Jersey, so they could get a quicker ferry hop and they'd be right over the river and they could go, right to work over there. Okay. A couple of other things that had to do with the improvement program here that was announced. It was bigger than just Penn Station. Obviously, you have to have a yard to put the train. So Sunnyside Yard out here in Long Island, was constructed. They had bought up the Long Island Railroad to become a subsidiary to also, they saw it as a lucrative thing back in the day. And so, in conjunction with the Long Island Railroad, Long Island City Terminal, Sunnyside was built right here. And then eventually there would be a provision. They hadn't done it yet, and it's not really the subject of today's talk, but over here just past Sunnyside Yard. I'm sorry, my cursor is disappearing here, but just past Sunnyside Yard is the way to the Hellgate Bridge, the New York Connecting Railroad. They had designs on doing it. They knew they wanted to do it. They were only doing this for now, but ultimately they knew that they were going to build that Hellgate Bridge, and it was all part of the Grand Master Plan. One other thing with the plan, not only did the passenger trains come into Jersey City, but a lot of the freight trains came here. It was getting very congested here at Arsenimus Cove and some other places in Jersey City. So they also built, excuse me, Greenville Yard over here with a shorter float bridge over to Bay Ridge with the New Haven. So the freight, they could bring the freight over here. They actually had some shared tracks with Lehigh Valley. But, Greenville Yard was built. Actually, a lot of the fill from Greenville Yard when they built this out into the water actually came from the dirt and tunnel from the tunnels and from Penn Station, and all that muck that they dug out of there actually became part of the land, which they built eventually built the freight yard on here. So you can kind of see here the overall scheme of things. Jersey City, but all these improvements, which the electrification helped drive, was all the electrification through here, through Penn Station, and then out to Sunnyside. So what kind of electrification? The next thing was they decided to do it. They knew we could electrify. All right. And the question was going to be, what kind of electrification do we want to have? And there's really two kinds of power that you see these days. There's really AC and DC. So the DC power has been in proven existence. Okay. So 1895, we talked about the B&O, New York Central, as part of their Grand Central electrification. They turned their stuff on in 1906. They bought the Long Island Railroad. And the Long Island Railroad, I should have put the date. I think it was about 1908, I believe. The Long Island Railroad started running to Brooklyn, down to Atlantic Avenue Terminal in Brooklyn, and they also had DC power. All right. DC traction motors are very well known. They're easy to control. You can take DC power from the third rail. You can put it through some relays and some resistors, and you can put it to the motors. It was sort of easy to control, for DC. So that was good. But the same thing with DC power, because it's lower voltage, it's got a voltage drop. All right. So, the power, DC third rail power operates anywhere between 600 and 900 volts, usually, depending on the system. There's a couple of exceptions out, west with the old Illinois Central. But in most cases, it's anywhere between 600 and 900 volts. And that power drops off. So you need a substation every couple of miles. That folks who ride Metroliners, New Haven, or Hudson Line or the Harlem Line or out of Long Island, you're going to have quite a number of substations every couple of miles to keep the third rail voltage up. All right. And not only that, because these trains draw such tremendous power, with the lower voltage means there's higher current, which means you need more conductors. So that's bigger steel, bigger copper, more material, and more expense that goes into it. And the Pennsylvania Railroad, although right now they really started with talking about the Penn Station electrification, really the design always was, we want to go longer distances. It's more efficient. It's much more efficient than steam locomotive. Steam locomotive is very labor intensive. It's not as efficient, energy wise when you're pulling trains. So if I'm going to do DC and go over a much longer distance, it's going to cost me a lot of money to do that. Okay. So what's the alternative? AC, alternating current power. So there's only limited AC development. So at the time, the PRR is really designing Penn Station. There's really only one AC electrification out there, and that was the New Haven Railroad's mainline electrification. So at first, when the New Haven was subject to that same 1902 law. So by 1908, they had to be running electric to Grand Central. So obviously they were running the third rail, but the New Haven also had designs for operating and eventually expanding their electric service. And they also saw the same problems with the DC power, much more expensive to go over longer distances for longer trains. So they decided from Woodlawn, where the junction with the New York Central New Haven, up to Stamford was the original electrification. A few years later, it got extended to New Haven. They decided to go with AC, which opened for service first in 1907. The disadvantage of AC was, in AC, you could, AC, they had some issues with the size of the motors. There's almost no experience with heavy haul. The New Haven Railroad is basically running, MU cars, if you will, back in the day, or there's really kind of like a fast trolley car, if you will. Okay. And there's still issues with the current collection. As a matter of fact, the whole electrification system, when the New Haven first rolled it out, we all know it today, it runs pretty good. But back in the day, it caused so many problems that the New Haven Board of Directors was actually trying to figure out what they're going to do to hold the Westinghouse Corporation accountable, because there were so many problems, things blowing up, things melting, things teething issues, things not working right. So many things to learn with it. And, but they actually did stick through it. So the PRR was looking at that saying, geez, there's a lot of trouble here. Okay. In the meantime, they were doing some testing. They set up 2 test tracks. One is on one of their subsidiaries called the West Jersey and Seashore, to try and figure out current collection. Okay. They had steam engines pulling things around, pulling like boxcars with pantographs on them to try and test different kinds of current collection. They actually did the same. They also had a second test bed up on the Long Island Railroad. I forget exactly where it was here, but they were running these testing around, and they were really having some difficulty at the speeds they wanted to go, the speeds they needed to operate to be able to get a reliable current collection. So they were fast approaching the time. The tunnels are being dug, right? And we still don't know what kind of electrification is going to go into the tunnel. So finally, 1908, the PRR said, that's it. We got to make a decision. This project is too big to fail. We cannot let it fail. So what they did is they decided, they took the safe bet. DC it is. Okay. So not only did they know what it was, they said, we'll do this, but one of the things they did do is they left provisions for later on in later years that they wanted to come back and put an AC system in the Penn Station. They left the provision when they constructed the whole thing, so it could be used for either. All right. So one of the other things the PR decided, though, too, was, they already had owned the Long Island Railroad. There was a power station in Long Island City supplying power to the Long Island trains that were, operating by this time. So what they said is, look, we've already got this fixed plant. We've already made this infrastructure. For some incremental cost, right, we can just add on to that Long Island City power station and to put additional capacity on there. When the Long Island trains come into Penn Station, the Pennsylvania Railroad trains are coming to Penn Station. They can all share a common network, and you're spreading your fixed cost over a much larger, much larger set of trains there. So DC it was. Okay. And they left the stuff there, they left the provisions there for later. So one of the things they did, folks will notice, the DD1 locomotive was one of the results. If you can see, these weren't like, trolley cars. These weren't elevated cars. You needed a lot of horsepower to pull the speeds and the grades you needed to pull through. So this was the design that the PRR in General Electric were able to come up with. The DD1 locomotive was actually 2 big electric motors driven through a jack shaft. Okay, you can see the jack shaft where the motor spins, and it turns. Basically, it's like a steam engine crank, if you will, cranking these wheels on the DD1 locomotive. The motors of the day, which needed the power, would not fit in the truck. So when you see like diesel locomotives today and traction motors today, the technology has just been so refined. You can actually shrink that motor down. The motors can take a lot more heat, a lot more horsepower. The technology just hadn't developed yet, so they wound up going with this. But these engines were great. They were very reliable. They worked well. The minutes of delay, I don't have the stats in front of me, but the minutes of delay, on a regular basis was such a small number, but they were just such a simple, reliable machine. Okay. They did have some issues, though, with some lateral forces on the rail. So they said, well, this is not quite the thing we need longer term, but it worked great for now. It was just so extraordinarily reliable. So, that's the, that's the thing that caused the first electrification to happen on the Pennsylvania Railroad, was the New York extension, as they call it. Okay. So that brings us up to 1910 when Penn Station opened. So what was next? Okay. What was next? So we're going to shift down the railroad to Philadelphia. So Broad Street Station was opened in 1881 in Philadelphia. And it really was at capacity. It was about 13 or 14 tracks, 1881. They expanded in 1893, but it was in a downtown situation. They had these big walls, elevated structure on the side of it. It was just very difficult to, you're not going to take out the real estate. It was very expensive to put more tracks in, to spread out over more city blocks to be able to get more trains in there. All right. And one of the things, once again, the phenomena was the commuter service, the local people from the main line, from Chestnut Hill, was really expanding. And the Pennsylvania Railroad was like afraid, because the long distance trains are much more lucrative than the commuter trains are, in terms of the return, in terms of the fares you can charge, in terms of the cost per mile, the revenue per mile to operate. Okay, and I mean that still holds today true. If you look at revenue per seat mile on an Amtrak train versus like even a commuter train, is still the same way. So they're very afraid. They didn't want these commuter trains to crowd out all the lucrative trains and the clockers and things like that. So they're trying to figure out what to do. So once again, they're still thinking long term for long distance service. And they said, you know what, we're going to go with AC. We're going to go with AC. And they actually developed a test section out actually right near where I live out here between Radnor and St. David's. They had a bunch of flat cars with collector things being pulled by steam locomotives back and forth, and they finally got what would become a pantograph design that they felt that actually you could operate at some level of speed with some level of reliability. So it's more about there's more than just the okay, we chose to go AC now, but you had to have a source of power. In a lot of places, like if you look at the traction companies that were around and big industrial businesses, everybody had their own powerhouse. They had to make their own power. One of the very fortunate things with the timing of all this, when the PR was looking at this, all right, this is at the turn of the century now, is that PECO, the Philadelphia Electric Company, was really looking to, they were building a new plant in South Philadelphia. They were bringing other industrial customers on the line, and they were looking, once again, electricity and electrification works best when you can spread your fixed costs out over many different customers, all right? And one of the largest customers that PECO had at the time was actually the Philadelphia Rapid Transit Company. There was a number of other industrial users coming online. And so actually PECO welcomed the Pennsylvania Railroad to show up, and plug into the Christian Street generating station, which is still sort of there. It's not being used for what it is anymore. But if you ever take the train to Washington, D.C. on the left-hand side, there's a big PECO plant on the other side of the river, and you can see it right next to Schuylkill Expressway. The plant itself is still there. But they were able to actually get a power supply that could supply power to both the Paoli and the Chestnut Hill East lines. And what they decided to go with the same voltage system. By this time, the New Haven system has sort of calmed down a little bit. So really the PRR really copied the innovative New Haven Railroad in terms of, how are we going to design this AC electrification? True fact. Okay, true fact. So the utility supply was there. And they were able to now, with MU cars, you could get a motor small enough to get in the truck of a passenger motor. So they said, we're going to electrify this commuter service here. All right. And, we will greatly reduce the amount of moves that the commuter trains have to make. And so we can still, grow that. They bought themselves a bunch more years of capacity by electrifying the terminal here and cutting down the number of steam locomotive servicing moves. The electric train could come in, 5 minutes later, they could change ends and going out the other way. One of the other interesting things that had to be developed, though, was, at the time, back in the day, the railroads all had these semaphores, and the PRR was a 4-track railroad, and you've got 2 signal masts on the one side to the outside of the track for this track and 2 signal masts the other way. And they found, once they put all these catenary structures up, that the semaphore view would be blocked. Okay, it'll be very difficult to see the semaphores. So not only that, but semaphores also were a maintenance headache, and they would freeze up sometimes in the winter. The snow or the heat could cause them issues to not work properly. It's a very mechanical device, very susceptible to the weather. And if a semaphore froze in a upright position, it could be clear when it should be down because the block is occupied. It could actually cause an accident. So the PRR actually developed their first position light system. It's a little bit different than the position lights we know today, but it was a 5-bolt system. I probably should have put a picture in here of that because of the electrification project. So they could hang a signal within the signal bridge, so the engineer could see it in his line of sight. It wasn't blocked by the beams. It wasn't blocked by the girders. The engineer can actually see it. This is, for the 1915 electrification. Just one fact, though, for the folks who see the position light signals, there's still a couple out here today. But the position light signal that most of us know on here, that really was refined later on in the mid-1920s. By about 1926, they had the standard developed as to what it is today. So this first one is a little bit different. So how do they do it? Look at this. Here's how they did it. Can you imagine this with OSHA today, right? So these pictures, I've got a couple pictures here. These are from a 1915 Pennsylvania Railroad employee magazine. Here they are. They're just hanging up in the air, working away at all this stuff. The wire is actually flexible. It is. It doesn't look like much, but you can support it. Some of these wires, can get, pretty stiff. I mean, it could hold a lot of people up there, as you can see. There they are, right? Look at them working. And guess what? All those tracks underneath are in service. They're up there working. Believe it or not, for the whole thing, from Paoli to Broad Street, it's just shy of 20 miles, and it's up to 4 tracks wide. The construction period was actually only 1 year. to put it all in, to put all this stuff in the service. It took them a year to do that. One of the things you can see here in the background, if you can see this shield here, that's actually one of those original position light signals that was installed with the 5 bulbs. You can have 5 lights up and down for a clear signal, 5 bulbs across. The concept is the same. It's just a number of bulbs in the way that the way the signal heads are different. So they actually call these the tombstone heads, if you can see the way they're shaped, unlike the circles, of the position lights as we know today. But this is, example of, of one of the original signals here that had to be installed so the engineers could see the signals for the electrification. So here's another example. Look at this. Can you imagine doing this today, right? Well, the one benefit though the PRR had is everything was steam, so there's no electricity on it. Okay, and what they did. So this is you can see an eastbound train here on number 1 track. This wire train is on number 2 track, and they've got this jury rig thing kind of going out across. Right as they're putting up the stuff, they're working above the traffic. There's no other electric wires for them to get tangled with here, but this is how they did it. They were able to do all this under traffic. These trains were going back and forth. Like I said, I can't imagine OSHA ever letting it happen today, but but this is what they did. Here's another look here at some of the signals as you can see them, in the background here. Okay, it's nice when you have a nice green, open field to work with. You can do this stuff. It takes us much longer these days when we change out catenary wires because everything else is already electric, and you can't shut the service. They didn't shut the service down. They got to keep the trains going here, but this was, they were in a good place at a good time to be able to get this done. So let's talk a little bit about how electric trains actually even work. Okay. So, when the power would come from PICO, from the power comes from the electric utility. It's not actually generated at the exact frequency or voltage that the trains need to use or that the catenary system can use. Okay. So, it comes from the utility. It goes into a converter in a traction power substation right here in the middle. I'll show you some examples here in a few minutes here of, what some of these converter stations look like. So it gets converted to the correct voltage that the trains can use, right? Then it gets sent out over there to the catenary, right? So once it's energized in the catenary now, then the catenary, the power goes to the train through the pantograph at the top of the train, which then goes down to the motors. Now, anything in electricity, for you folks who are electricians on here, electricity has to be in a big loop for it to go back around. So the way this works is that the power is used in the motors, and it actually gets returned through the rail, in the rails through a conductor, and then it goes back here and winds up back in the substation to complete the loop. All right, so that rail is sort of the ground, but never step on the rail, because if you're in the wrong place at the wrong time, there could be 11,000 volts going through that rail electrified territory here, 12,000 volts if you're in the wrong place at the wrong time. So think about it as one big circuit here. So the PRR was very fortunate. They had the power from the PICO's utility, converted it up, AC power, with the higher voltage, because we're running 12,000 volts now at 25 cycles. You need less substations here. In the PRR system, there's a substation that goes in there. It's probably about every 10 miles or so, versus about every 3 miles or so when you have a DC system. So we talked about Paoli. Paoli was the first to go. 1915 is when that opened. So it's over 100 years old now. All right. It's actually 108 years old, a little over 108 years old now. The second line to go is Chestnut Hill, 1918. And then things sort of took a hiatus around here for World War II. All right. But the PRR said, listen, we're still running into congestion issues. Broad Street Station is still congested. So really, in the 1920s, the Pennsylvania started developing this program called the Philadelphia Improvements. What are we going to do? These suburban trains are taking up so much space. So that's really in the 1920s is when the concept of we're going to build 30th Street Station, as we know today. Where 30th Street is, by the way, where all those platforms are, there were a couple tracks down there. It was all stockyards. It was like a miserable, nasty place. The trains went over on the bridges over the river to downtown and a couple different places. But really, it was in the 1920s when Broad Street was still bottom of congestion. We're going to build 30th Street. We're also going to build an adjacent station for the commuters to get downtown. We're going to call that Suburban Station. And we will electrify all these short commuter lines in Philadelphia here in order to open up Suburban Station downtown and move these trains downtown and get them out of Broad Street and hopefully eventually get them into and get the long distance trains over to 30th Street. So one of the debate that was actually going on at the time in the 20s, like, where do we want to expand on next? Okay, where do we want to expand next? And the mountain over Horseshoe Curve and Gallitzin, all those places was really clogged with freight trains. It really was. And they're trying to debate, where do I want to put my cash? Do I want to put it into Philadelphia, or do I want to put it into electrifying over the mountain? And they didn't have no money at the time to do the whole thing. And they were trying to decide, well, they could electrify this one section, but it really wouldn't be that efficient, actually. You already had PICO, you already had some efficiencies, and with all the trains here with the efficiencies, they actually decided to, with the Philadelphia Improvement Project, we're going to do the rest of Philadelphia and just not do, over the mountain. You're going to see they had a couple decisions to make again and again about what they were going to do, but it never wound up happening here. So, by September the 30th, when Suburban Station opened, all the trains came out of Broad Street Station. We're now starting to get into depression time here. And, between the city of Philadelphia, the PRR had some challenges with, the city of Philadelphia actually needed to do some things with the Philadelphia Improvement Project too. We sort of stalled here, getting out of Broad Street Station in 1930. So 30th Street opened up in 31 and 33, depending on which section of the station we're talking about. But really, we started getting the status quo for here until the city of Philadelphia could do some other stuff, in the 50s. So the PRR said, we've got this in 1930. What else are we going to do next? So really, this is really the period where the PRR started to really kick in the high growth then, okay? The first thing was, we're going to first put down Catenary up in New York. The commuter business is growing again, and they actually turned on the electrification between New York and New Brunswick in December of 32. That's when they started running it. There's a couple dates here, folks. There's some conflicts in historical records, so I got to look to correct some of this. So it shows only a month later they went Philadelphia to New York. I'm not quite sure of that. I'm trying to do my best here to get to the bottom of it, but there's some conflicts in the records here. But anyway, New York to New Brunswick first. Then remember, we're already going to Trenton, right? We were already going to Trenton back in 1930. So by 1933, they just had to fill in that 25-mile or so gap between New Brunswick and Trenton. Now we were able to go Philadelphia all the way to New York. As a matter of fact, not only could we go Philadelphia to New York, but remember, we were also back in 1928 go to Wilmington. You could actually run now an electric train from Philadelphia all the way to Wilmington, which was done for a short period of time. And then a steam locomotive was put on the train at Wilmington to take it to DC. A lot of folks don't realize that there was actually some engine changes at Wilmington, for a little while here. As you can see, though, the lower level of 30th Street finally opened in March of 33. The Washington extension opened up in 1935, and including they began extending the freight line, the freight tracks out to Pot Yard, got electrified also shortly after that in 1935. All right. So now we're in the depths of the depression here. What can I do? Can I do something? What can we do? They actually decided to go forward, with some other funding that they were able to get and electrify the whole West End, including the Trenton Freight Cutoff, the A&S low grade line. I'll show you where that is in a minute here. The Port Road, we call it, the Columbia branch, all these other branches, up to 1938. So really, 1938 is really that peak year of PRR electrified mileage. Is really the extent of what it was. Okay, right here by 1938. So this is a map. Some folks have seen it before. This is just a little bit of post-war map. As you can see, the electrified tracks, New York, Newark. There's a couple of other branches on here. Trenton Freight Cutoff. Here's the main line, the Paoli. Here's some of the freight lines. It goes all the way out to Enola on this side of the river. The passenger trains went to Harrisburg on this side of the river. There's Port Road, still used by the NS today. Obviously, the wires are gone from Perryville, down to Washington, D.C. So you can really see, this was really the peak of the Pennsylvania Railroad's electrification with all these different spots, that are out here. So I'll show you a couple pictures here we got out of the collection of them building some stuff. This particular picture, which is interesting, the PRR, remember, like I said, always had designs on, we want to do long distance. We want to do, we want to go longer distances. So this is a place called Shore Interlock, and it's in Philadelphia. Some of the folks may recognize what's SEPTA's Market Frankfurt L, over the track here today. This is looking east. But if you notice the pole, so like the wires are not all up in service yet. So this is pre-1930 when they turn on the Trent electrification, right? So, but they already knew, if you look at all these extra transmission lines up here, so each of these two insulators equals one transmission line. So you got 1, 2, 3, 4 transmission lines all up here. So they knew, you don't need 4 transmission lines to go run a couple locals to Trenton. They already had designs. We are building for the future here as we build this. We're going to build a transmission network in there. We envision long distance trains going to New York. We envision freight trains going on this, and they were clearly building for the future, as they are constructing this, under traffic here. Okay. Another picture. Actually, this is up on, we call it the High Line. This is the curve. Actually, right over here, right in the Jersey Meadows, was where the original local engine change place was going to be built by the PRR. Just outside the tunnel is right around here to the side. So folks may know you're traveling into New York City from Newark. You kind of come around. There's a big right-hand sweeping curve there, and you come into the tunnel this way. You can see they're starting to put up some poles in locations, but the third rail is still here. Those DD1 locomotives are still pulling trains, between Penn Station and Manhattan Transfer. Here's another interesting picture. This is at a place called Grundy Interlocking. This Grundy is located in Bristol, Pennsylvania, and you can see a couple things to take a look at here. First of all, you can see here the semaphore signals. These are old semaphores, which are eventually going to get covered up by all the catenary structures and everything. They're starting to hang some catenary here. But you can also see here are the new position light signals that are being installed. Can you see them here? Here's the backside of the new home signals for Grundy here. Here's some automatics. Looks like they're going west on tracks 3 and 4. This is the 1926 standard. So this picture is probably taken. This is probably around 1928 or so is when this picture was taken. But you can see how the railroad is in transition here, from one technology to the other. So ultimately, when it was built, this is a Pennsylvania Railroad picture. I'll see in the Q&A session later on, see if anybody can recognize where this picture was taking place. I might have told you guys before, but anyway, see if anybody remembers where this picture was taking place. But you can see a couple different things here. You can see this is the catenary system we're used to. We call this the trolley wire here. It rides actually on a trolley. We still call it the trolley wire today, or actually a more modern term is a contact wire. You can see the transmission wires up here. And I'm going to talk a few minutes here. I'll talk about what that transmission network is and how we step down the power. And then there's actually one other type of power over here, the 6600 volt signal line on the poles here. That's actually at 100 cycle power. And that's the power that we use to drive the signals up and down the road. It lights the bulbs up. It drives the interlocking machines. It drives all the track circuits. It drives battery charging for batteries for the signal circuits and everything. But this is a great picture somewhere in the PRR. So in the Q&A, see if anybody can figure that out of what's out there. So one other fascinating picture. I just absolutely love this picture. I just got to show everybody this. Okay, this is Odenton, Maryland. Okay, so for the folks who are familiar where Odenton is today, the Odenton station platform is about right here. The high level platform about here and goes north. The south end, the station building itself is right over here. And what we're looking at, if you look at this catenary here, is coming across. Like, what is that, right? So this is actually the Washington. All right, somebody here is going to correct me. The WBA, Washington, Baltimore, Annapolis interurban line. Okay, and guess what they ran now? So the PRR is running 12,000 volts AC, right? But they're running probably 600 or 700 volts DC. So that's a problem. So it's one thing to have like wheels going across a diamond, climbing across the track, but what do you do when you have different voltages, and how do you keep, you don't want to melt that interurban car with 12,000 volts of AC, or you don't want to put DC and blow everything else up on the PR side. You can't have the power cross. So this structure here, and this actually predates the installation of number 1 track down there. So 2 and 3 track are installed, but the other track, the third track, wasn't actually installed down there, I believe, until sometime in the 50s. But there's actually this structure here, if you can see, there's a structure, and this is actually turned sideways, and it's actually running below a bunch of the trolley wire here. Okay, so this structure, so any interurban would come across the line here. It's riding on its 700 volts. It touches this structure. It rides underneath the trolley line. It rides underneath the PR trains, goes across, and then it keeps going on its way. And when the interurban is clear, the signals are put back to stop. This whole structure here rotates. It actually pivots. It pivots right here. There's a shaft that pivots 90 degrees, and therefore the structure goes this way then, and it's actually lower than the trolley wire, but it's between the trolley wire. So now the Pennsylvania Railroad trains can go north on 2 or south on 3, and they can pass by it, and the two voltages shall never meet. Okay, so everybody thinks about diamonds and light rail that try to cross 700 volts with 12,000 volts, and that's why I just love this picture. It's such a great picture, of things that go in, and why I say railroading is truly, electrification and railroading is truly the fourth dimension. It really is. You don't even think about that. How does all this stuff work? It truly is in the fourth dimension. So So obviously this is what the PRR designed. All right. I had to throw one GG1 picture, and everyone wants to see the GG1, right? One GG1 picture. This is actually right there in the Bergen Hills much later. The train's just out of the tunnel of Manhattan is going to that spot where I just showed you the picture with the third rail only. But this is, what we all know for years, for many years, and how the PRR supported all this. You can see the transmission lines up here in the catenary and the trolley lines, and the signal line is actually is right on top of it. You can't see the signal line. It's actually right on top of the photographer there where the signal line is. So let's go talk about then, how do we control the fourth dimension? Okay. Because just because you have it, that's fine. Just like, you can see a train on the track, but you got to have control of it. You got train dispatchers, tower operators. Well, you have to have the same thing for the power. So in order to control power, the several things have to be done. So you have to establish power director offices, and they actually are.
Excuse me, Chris.
Yeah.
There's a question that I think is germane. I want to just put it out here
All right,
now.
no problem.
Regarding the when the interurban crossed the Pennsylvania Railroad, wasn't there an issue with the return path through the tracks at the Diamond Crossing?
So I believe there shouldn't be, because I believe they would probably set some stuff up. There's some other switches down there too, I believe. And probably what you're going to find, like at all diamonds, you find insulated joints around that keep power from flowing one way or the other. So I can't quite see it here, but I am positive they would have had some other insulated joints down there to be able to make sure that the power gets to the right spot. Okay. But I will say one thing, though. If you want to think about one thing, think about Penn Station, New York today. Okay. In that today, you have 12,500 volt or 12,000 volt AC trains running at 25 cycle power. And today we also have Long Island Railroad trains running at 750 volts DC also. And so, what they're able to do is to tune up their, believe it or not. And then you got 100 cycle signal power in the track too with signal voltage, which is crazy. You wouldn't believe how tricky it is to make those signal systems work. And to also pile on to one other thing, I'm sorry, I'm thinking out loud about this, right? Actually, in New York, from a place called Hunter, okay, to a place called Gates, all right, so most of the signal power that we have is all at 100 hertz, right? And 100 hertz signal power for the cab signals in the track is done to keep it from interfering with the traction power, and it keeps it away from, we call it harmonics in the power. So the problem is, with the 100 hertz power in the DC trains, there's an issue, and you could actually cause some false proceeds. The PRR discovered this. If you have a DC train in the block followed by an AC train, all of a sudden you start getting, you'll actually start drawing signal current through the DC transformer of that train, believe it or not, into the AC train. So we actually modify the signal power. A lot of people don't know this. Is actually running at instead of running at 100 hertz up there, it actually runs at 93 1/3 hertz from Hunter to Gate, and it actually knocks out the harmonic. And so you can actually mix up the DC rail return and the AC rail return too. So I'm sorry I had to get the answer. So there might not have to be too many things. There's got to be impedance bonds there to protect everything. So you just don't backfeed certain things, but you can actually get the return to work if you got your bonds tuned up the right way. How's that? I don't understand it myself. Magic, right? So let's go to the power. So power director office, you have to have power director office. So the PRR had 5 of them. One of them was New York, and that controlled the DC electrification in New York, which is still there today, right? You had the Jersey City office. So when the AC came to Jersey in 1930, the Jersey City office actually controlled the AC power from there. Philadelphia, the Philadelphia had the original Philadelphia electrification, and later on, obviously, it expanded much more out there. There's a Baltimore office and a Harrisburg office, all in 1938. So not only do you have the power director is responsible, they work in close proximity with train dispatchers and tower operators. But now on Amtrak and the PRR system, there's actually one extra thing. We actually also have a load dispatcher, and I'll talk in a few minutes about what the load dispatcher does. But the load dispatcher, they actually talk with the different utilities. So, for example, the whole catenary power grid from Washington to Washington to Harrisburg to New York is all phased together. It's like one big giant circuit. So, and it's actually fed by up to 6 different utilities. I'll show you what it is in a minute, but the load dispatcher has to manage all of that. So just remember, power director controls power on the tracks with the train dispatcher. The load dispatcher controls that transmission network. So let's go look at what that looks like. So this, controlling the fourth dimension, here it is. This is the original power director office that was built in 30th Street Station, okay? And, you know, some of the things you can see here, you can see some of the tracks in Penn Coach Yard, the QN Yard, there's Powell Yard up at the top. Here's 30th Street Station at the bottom. You can see going up to Zoo, and you can see a lot of other things here out towards Harrisburg. So this is the original PD office that was it was actually located in the 4th floor of the North Tower at 30th Street Station, okay? But so back in the day when power directors offices first came out, we didn't have modems, we didn't have remote control over things. Okay, we had phone lines and telegraph lines, but it was difficult to control some of this. So they had control and command, but what they had to do was talk to folks in the towers, just like a train dispatcher was in a central office, talk to the tower to give out the train orders. A power director was in the office and gave out power instructions to tower operators. So this picture here, actually, thank you, George Pitts, if you're on the line. So I got this picture from George Pitts. This is 1974 in Perryville Tower. So not only was there an interlocking machine, but this was the power machine, and you can see a bunch of levers here and circuits that the block operator or the tower operator would actually control that. So if you were going to become if you were a block operator, tower operator in training, you would go through and qualify the signals and the switches and the tracks with a train dispatcher. But then before you could work, you actually had to go also to the power director office and get questions about what each and every one of the physical characteristics of these knobs and meters and switches do, and where the trolley circuits went and what it meant. You would have to be qualified, you know, on that too before you're allowed to work. Okay, they were in a lot of these towers. Now, in 1938, though, was the pinnacle of the PRR electrification. There was actually remote control technology that became available. You know, CTC machines started becoming available, you know, in that period of time, and power control also could be there too. So this is a picture here of the power director office in Harrisburg. Okay, it has since been closed, you know, but they could actually control a lot of the substations remotely. So you ever look at the towers on the Harrisburg line, whether it's Thorndale or State when it was there, or Parksburg when it was there, they didn't have to do that because the power director here in the office could actually control all this stuff from their network of panels and switches. Philadelphia couldn't do it, but Harrisburg could. Okay, and it depends on really where you were and what the interlocking was. Some had control in some places, depend on when it was converted. And for the folks who don't know, the NRHS, the Harrisburg chapter of NRHS, has both a museum in State Tower, where in Harris Tower, excuse me, which is the west end of Harrisburg Station. They did a phenomenal job to restore it. They got a computer hooked up. It's computer simulations. I highly recommend the visit. They just opened up this. So this was the Amtrak property here, but it has been leased out to the NRHS Harrisburg chapter, and they have just restored this, and they're in the process of doing the same thing. In fact, I'm helping them out with some exhibits here. So if you ever get down the Harrisburg way, make sure you look it up. Check these people out. It's a great working exhibit. They've actually even got some of the original Art Deco light fixtures that are still up there. They're cleaning up and hanging them in the office here. So, okay. But there's a whole command and control system we don't even think about, you know, with the power that goes behind how you keep the electricity running to those electric trains. All right. So one other thing is the load dispatcher. So this is the load dispatcher's office here. This is actually the load dispatcher's office in Philadelphia. And you can see there's some other simpler things. They're actually controlling the transmission network here. And they worked in concert. They were right next door to the power director's office. Actually, I'll show you a modern picture of this room here, what it looks like now. But that room is still there. It's a little bit different configuration. I'll show you a picture in a few slides of what it looks like. But they actually are tied into all the different utilities. So the northeast, south and northeast corridors, we know it is fed by 6 different utilities. They're all phased together, and the power director and the load dispatcher balances the power. They can draw more power from New Jersey and less from Philadelphia, and more from Philadelphia and less from Baltimore. Okay. So, you know, they've got control over this whole thing. So just to show everybody what this whole network looks like, I made up a little diagram here. This is really the transmission line at the pinnacle of the peak in 1938. So these are all 138,000 volt, 25 cycle circuits. Those are the way up high wires. There's usually 2 of them on each pole. You know, 2 legs is one circuit here. But you can see, you know, Sunnyside. So you can hear Sunnyside Yard, and actually there was a converter station at Sunnyside where from Con Ed fed into was originally PRR from Long Island generated power descended over here. It's Con Ed now. You know, for the folks looking at these are the 1938 names as it stood in 1938. All right, Metuchen, Power Feed, Pico and Richmond, Pico at Lamoken, Consolidated at Bennings, and then you know, Pennsylvania Water and Power Company at Safe Harbor Dam, which I'll show you the dam in just a minute here. But this whole network You could go Harrisburg to Parksburg this way, Harrisburg to Safe Harbor this way, down Safe Harbor down to Perryville this way. There's actually some things. There's actually people didn't even know over the Chester Creek branch. It's still there today. There's a feed from the Lamoken sub that goes over 10 miles of ground where there's no track out there. It's not even over the railroad to Lenai, and then feeds the back. It back feeds the SEPTA Westchester line. Okay, and then it comes into Philadelphia this way. The Schuylkill Valley branch. It goes here from Ernest to Trenton. That line is still. I'll show you some pictures of it. That line is still there today. So really, almost all of this is still in, except for the South Amboy to Midway piece is gone, and the Ernest to Trenton piece is gone, and Pot Yard is actually not electrified anymore. But the rest of it, it's all still there today. All this stuff is there, controlled by these load dispatchers. These load dispatchers, they figure out how much power they're going to buy from each one of these things. Like, for example, the dam over here, it depends, you can get, depending on the power, it depends on how much water is in the dam. Sometimes it's low water, you're going to get less power. High water is more power, or even when you get more power, then it's going to be cheaper, from there. They can schedule the power. It all has to go into it, to make the trains run. So, couple things. Here's these transmission lines are actually still live today. These are, so the picture on the left, this is the Schuylkill Valley Bike Trail. It's me out right on my bike one day, and the top three. So if you notice the railroad lines, because we run single phase power, there's two transmission legs. So this is one transmission line. This is the other one. And this is how we backfeed from Safe Harbor into Philadelphia, because there's no transmission lines going through Bryn Mawr, Paoli, places like that. But we actually go up a lot of the bike path here. Okay. Middle of Maryland, there's 20 miles of this. There's 4 transmission legs on this that come from Safe Harbor Dam, come all the way down to Prairieville. If you're driving I-95, right there where the toll plaza used to be, in Maryland, you'll see this big transmission line coming over the hill. That's actually all Amtrak transmission power. This is actually all Amtrak, transmission power feeding the Northeast Corridor from that dam. Okay. This is fascinating. This is a different bike trail. This is on the former, I call it the A&S low grade. Great bike trail for those who, are local in the area. I highly recommend it. 2 power lines crossing. Look at this. These are all Amtrak power lines. You're in the middle of nowhere. There's no Amtrak trains for 25 miles, from this location. But here's your 4 lines going down to Perryville this way, and here's your 2 lanes over here going this way to feed towards Parksburg on the Harrisburg line. All right. Here's a picture of the dam. Great bike trail. They just opened this last July. Highly recommend it for you bikers out there. All right. Great view of the dam. Is fantastic. You can actually ride along. The track below is the Port Road branch. The NS still runs freight trains, although most of them are down there at nighttime because they go out to the Northeast Corridor. But this is an active NS line. But this is the old low grade, which is abandoned. Low grade, which is a high. Go figure, right? But the power lines still run over this, being fed from the dam itself. There's 12 water wheels in that dam, and water wheels 1 and 2 actually generate power right at 25 cycles to go right into the Northeast Corridor power grid. 3 through 12 actually go feed 60 cycle, which is commercial power voltage. So I'm getting close to the end, Dave. All right, this will go quicker now. So anyway, PR did this, but now, what are we going to do for high speed? Really, one of the big events for high speed, in transportation was 1964 was the opening of the Tokaido Shinkansen line. Okay. And the U.S. said, we're getting beat. We need to do something. What are we going to do? So, they was signed, the High Speed Ground Transportation Act was signed in 1965, which ultimately led to the Metroliner service in 69. But, this was really the beginnings of a high speed, and the PRR catenary system, was what made it work. So, back in 65, so high speed testing, this is back then where we still test high speed in the same place. In the US DOT was able to place a quick order for Bud for 4 MU cars. These are, Jersey, SEPTA had just bought about 55 of these cars from Bud, and the US DOT sort of added on just a few years later to the order because they could get these things quickly. And they got these trains running around. They got them up to about 156 miles an hour or so, give or take, while the Bud company was developing, other production cars. Once again, here we are up to 156 miles an hour, on this original, here it is PR catenary with there's those 1926 position light signals right up there. Okay. So once we proved, okay, the track can handle it, the catenary can pretty much handle it, that led to the development of the Metroliner cars we know. There were 60 of these built in the 60s, went through a lot of testing. They had a lot of trouble. You know, a lot of electricity, a lot of electrical issues with them, some compatibility issues, you know, because some of the cars are made by two different manufacturers. You can tell by the pantograph here. These are Westinghouse cars. Some other cars I'll show you in a minute had different style pantograph. They were the GE cars, you know, and sometimes they didn't play nice together. So as you can see, we all have cars of the same kind here because that sort of really put a hamper on the testing here. You know, but these cars, they were, you know, they really wanted to get up to, you know, what can we do to go beat the Tokaido Shinkansen train? You know, they were really able to get up to about 164 miles an hour, but there was no way with all the electrical problems of these cars, it was never going to get into the design speed. So really, you know, they tested it. The PRR, these cars were delivered to the PRR. They actually never made it in service to the PRR because the PRR went away on February 1st of 68. But in January 69, the cars were finally able to go in service under the Penn Central. So remember that pantograph's different. You can tell that's a GE car with that Bailey pantograph on there. GE also made the food cars, and they also made the club cars as well. But you know, January 1st, 69. So it became really, you know, a 120 miles an hour service. It really became populated. It was successful. It actually was able to show you could draw folks back to the trains. Okay. Turbo train up the north end was a compatriot. It was you know, sort of a companion to that. You know, but the Metroliners, you know, due to a couple reasons. I mean, although they both trains had their trouble, the Metroliners seem to do fairly better than some of it. But you know, the electrical issues continued to plague the trains as they ran out there. You know, limited to really truly the number of trains that could operate. Obviously, the Penn Central was still around, but you know, Amtrak took over passenger service in May 1st, 71, in trying to figure out what can we do to improve these Metroliners, you know, because we had so many problems with them. They really were putting a crimp in the service in terms of, you know, the capacity and the reliability of the service. So, you know, there was a project worked on early on to send a couple of cars back to General Electric. So you can see in this train here, if you see in this train here, there's a hump on the roof of one of these cars. You know, electricity and water generally don't like to mix. You know, what was happening, there's a lot of electric components underneath here was getting clogged with snow and ice, causing shorts and grounds in the system. So General Electric took a couple cars as an experiment and rebuilt them and moved a lot of electrical components up to the roof to get them away from the dirt and the debris and the ice down here. And it did make them better. It didn't make them great, you know, but it made them better. And you know, Amtrak was able to do some stuff to get some number of trips increased, but it still, you know, wasn't quite, you know, what Amtrak wanted. But once again, 120 miles an hour, it was able to kind of do it on a day in and day out basis and do it pretty well. But Amtrak wasn't quite satisfied with it. So, you know, one of the things that Amtrak began testing was the Swedish RC4 locomotive in, you know, the late 1970s, and it was very successful. The Gs were having issues. They were good, loyal soldiers, but they were tired soldiers. So the AM7s came around, and Amtrak really loved the AM7s, you know, when they came out. Now, one of the things that was happening now at the same time was that the superliners were also being delivered out west. And the superliners, you know, starting in very late 70s, 1980, 81, the superliners began cascading the Amfleet long distance coaches out of those western trains, and they all of a sudden became available. And so Amtrak started experimenting. Can I use some AM7s to haul the Amfleet long distance Amfleet cars and use them? They were much more reliable than the Metroliner cars. And so really by 1981, all of the Metroliners were downgraded into the Keystone, what we know now today is the Keystone service. And it became a very reliable product. You know, Amtrak was able to consistently deliver the trains, you know, run them on a regular basis. The speeds were actually, you know, the Metroliner speeds were degraded. They actually even had Gs operating at one point. Their speeds were down to 90 or 100. But consistently, Amtrak was, you know, back in the 80s, Amtrak was able to get on this catenary, you know, speeds up to a solid 125 miles an hour. So what's next? How do we grow the business? What can we do to make faster? Amtrak also had visions on the electrification system was great. It was efficient. The trains could go fast. It was cleaner energy, much faster trains. You know, we always envisioned, you know, okay, let's go extend the service to Boston. What could we do to do that? So Amtrak began looking overseas. We had it in 1993. We had a couple test trains out here. One of them was the X2000, which you see on the left-hand side of the screen here. And one of them was the German ice train. You know, we bought a set from Deutsche Bahn. You know, the trains with the X2000 was a fantastic train. It did all sorts of stuff. You know, if anybody ever takes a ride in Sweden between Stockholm and Göteborg over there, it actually looks like the shoreline between New Haven and Boston. There's curves, there's freight traffic out there. It's not like this dedicated TGV line, and it's actually a great train. The Deutsche Bahn train, the ice train, didn't fare as well. It was rough riding. It was really meant to run on a dedicated right of the way. Amtrak does not have a dedicated right of way on here. So in reality, the ice train sort of went back early. The X2000, really helped us learn a lot of stuff about high speed. What do we want in a set? Put a procurement on the street, and then in the mid 90s, we awarded the contract, for what was to become the Acela train, which finally got launched in November 2000. So the train that we got, it was developed, a consortium between Bombardier and Alstom developed this train. It operates at 150 miles an hour, very reliable. They bought 20 sets. We're down to 16 right now since after COVID, and some of the sets, just because the parts available, had to be cannibalized, to keep this service running. But these have been very successful. But then, of course, we are now looking to go to, even higher speeds, and the Acelas are wearing out now. They're getting old, and so we're replacing them. So, we did develop another RFP, a couple of years ago, put it out in the street. Alstom got the contract, and now you're working on developing the new Acela, which will be the replacement, for the legacy Acelas, planning to come online in 2024. So this train, here it is, operating under that 1938 Harrisburg Catenary. We have had this train up to 165 miles an hour operating on some of that catenary. The catenary system has laid the way, to be able to do, a true high-speed operation here. So before I finish off here, I'm just going to show you a couple more things. We're going to talk about the catenary and the power and how does it get to the train. This is less about the train. This is more about the wires and technology here. So a couple ways we can bring the power onto the network is that the power stations make the power a certain way. So in the top left-hand side, you see a rotary converter here. Okay, we have a handful of these on the system. We have these Lebokin, I guess we have these Lebokin, and the water wheels are also rotaries. And so, we take the power from the substation. The one side is set up to be a 60 cycle motor. The other side is really set up to be a 25 cycle generator, and it spits out the other power on the other side. It's a very great thing. It's high maintenance, but it's a very stable influence on the system because mechanically it's rotating at speed and keeps the power very stable. Okay. We also have solid state frequency converters, which are great. They can get into phase really quick, but they got some issues. They're cheaper. They're much less maintenance. But just like, there's some folks who believe in an analog, synthesizer or a digital synthesizer. Analog, folks always say, is better. There's good and bad about both things. It's cheaper. It's easier to maintain, and to power on the system. But, what we found a combination of both. It minimizes some of the maintenance cost, but it also makes the power a little bit more reliable coming out of this. And then obviously, there's also hydroelectric power, which all goes into the system. This is actually a picture inside the Safe Harbor Dam. This is what these water wheels do look like. 1 and 2 are actually the ones that generate right at the railroad voltage, and the rest of them generate at commercial voltage here in the station. So it's just there's a lot of behind the scenes stuff. I mean, think about the electricity that goes from here, goes through all those transmission networks, right? Goes to the transformer on the side of the tracks, goes into the catenary power, goes to the pantograph, goes into the train, goes to a transformer in the train, goes to the 480 cable, goes to a step-down transformer, so you can plug your laptop into the outlet on the train. It all comes from here, if you think about it. It's a long way for that power to travel. So let's just talk really quickly about just a few more things. Here's actually a picture of the modern load dispatcher office. Remember the old one I showed you? Well, this is what it looks like now. We can digitally see everything. We're tied into a whole bunch of stuff digitally, using the SCADA system, supervisory control and data acquisition system. It's a standard power system, but they oversee everything here so we can balance all the needs. And, this is actually how we manage it today. It's really, truly a fourth dimension. Nobody sees these guys up here in this dark room. This is located in 30th Street, and they oversee all that power between New York, Washington, out to Harrisburg, and also the stuff that's happening at the dam here in Philly. So one last thing, we'll do one little lesson here, Dave, then I'll be done. Catenary, all right? We talked a little bit about this before, but here's a regular piece of catenary, and just like folks know metal, right? When it heats up, metal expands, and when it cools off, metal contracts. So let's suppose here's a day, it's 60 degrees outside, there's no wind, no ice out there. Our catenary wire, we have it set up to be about, if you see here, it's about 5,000 pounds of tension. That keeps the wire nice and straight and taut, for the train. But what's going to happen when the temperature changes, right? So when the temperature goes to 110, all of a sudden, look, you went from, 5,000 pounds of tension. Now you're down at 15, and the wire starts to sag. And that becomes difficult for the pantograph to keep up with. In some cases, the wire sags too much. You'll come out from underneath the wire and you rip the whole thing down, okay? Which is a problem with the catenary. Then on the other side of it, let's suppose the power goes to 0 degrees. All of a sudden now your tension went from 5,000 it's up to over 7,000 pounds of tension, when you get real cold. And that can cause issues. You can snap the wire, it'll snap in 2 pieces. You put a little bit of tension on it, you can have a problem with it. So this is fixed termination catenary because it doesn't move, but the tension the tension changes, depending on what the temperature is, which can be problematic. So one of the things we're doing is we're taking some of the poles and we're converting some stuff around. We're putting in constant tension catenary. And this is what you see up in New England now. You'll see it in some places down here as we finally start to replace some of this stuff. There's a section of wire, and it's at about 4,400 pounds. There's a counterweights and a pulley. So here we are. Here's the same 60-degree day with 4,400 pounds. Now, let's suppose it's going to heat up to 110 degrees, right? But guess what happens? There's those weights that go down, and you still got the same 4,400. There's a nice smooth track for that pantograph to ride on, nice smooth surface, and it's good. And the same thing is when it gets cold in 0 degrees, right? You're going to keep the same tension on it. Those things go right back up in the air again, and therefore you maintain the same constant tension, in everything, and then it really provides a much better way to do it. So here's how it looks in real life here. So in some places, like the picture on the right is some of the folks some of the pictures you would see up in New England. You'll see the pebbles, you'll see the counterweights. They keep it at a constant tension. On the left is a different place where it's fixed anchor point. You can see it doesn't move around. It's just fixed, and sometimes if you're not operating high speed, fixed is just fine for like a yard or places like that. You don't need much, but but it's some of the systems that we do here. So the last subject is one of the other things we're doing. Here's those 1933, 1932, 1933 poles in New Jersey. This is taken just right out of New Brunswick, New Jersey. We're actually keeping the poles because there's miles of old wire up there, right? And we're actually changing these, steady, we call them SAP assemblies, SAP, but it's steady and pull-off assemblies. And we're actually changing this. So we're changing it so that one track can operate independently of another one. So if one train goes by on one of the tracks, all 4 tracks don't bounce together. And we're actually able to raise the speed of the track, where we do that on this original catenary system. So to review here, just a couple of kinds of catenary we have. On the fixed tension, which is the original PRR, we can get up to 135 miles an hour, on that. It varies with the temperature, becomes rigid, and there's miles of it. There are just miles of it everywhere, and it takes so long and so expensive to change it out under traffic, but we've done it in some cases here. Constant tension, the modern standards, where there's new construction, like New Haven and Boston, was all built to constant tension. Metro North and Condot replaced all of their catenary. The whole New Haven line is all constant tension now. And we've got sections of it in Jersey, and we're working on to add some more sections here. It takes a while, there's miles, but you can get 160 miles an hour out of it. In the meantime, on that old Pennsylvania Railroad stuff that we've got, by putting those assemblies in, we found a way we can actually raise the speed from 135 even up to 145 on that original 1935, 1938 wire. We can get 145 miles an hour out of it. Speed quicker with less investment. It doesn't get us quite to 160, but every mile an hour counts. Okay. And these are all sorts of things that we're doing. The Keystone was laid by the Pennsylvania Railroad way back in 1915, and we are still building on it. You see the many different types of equipment that have run on it, and you never know what kind of equipment could be running on it in the future. So, Dave, I am at the end of the talk here.
Gonna explain that picture, Chris?
I don't know. It's just a train on the track, right? What's different about that picture, right? So seriously, for the folks who don't know, this is probably the only time that I'm aware we actually ever use an ACS 64 electric locomotive to go haul superliner equipment. Yes, it does fit on the wires, not everywhere. It will not go to Penn Station, and it will not go some other places. But yeah. So you never know. You never know what you're going to see under the wires. There's been a ton of different things under the wires, and that's yet another one. So. Here we are, Dave. Question time.
Okay, well, we have over 100 people
Wow.
between the Zoom and got about 8 or 9 on Facebook. So obviously a little impractical to let everybody in at this point. So if you have questions for Chris, please type them into the Q&A, and I'll try to present them. So if you have questions, put them in the Q&A, and all the high praise for Chris can go in the chat. because it's changing really quick here. There was one, let's see. There was one question that a person said he read that Amtrak wanted the X2000, but it says that apparently Canada gave huge subsidies for the Acela. True or false?
Well, mostly true. So the X2000 was a great train, okay, but there's lots of great automobiles out there, but you got to be able to buy what you can afford. Do I want the big old fancy, do I want a Ferrari? Well, that would be great. It would be fun to drive, but guess what? Maybe I can only afford the Chevy. So the X2000 price was way higher than what Bombardier was able to offer us for whatever deals they had. I heard different things. I don't have all the quite personally have all the facts, but it definitely was price was one of the factors that went into it. In the X2000, just the price was not even close, to what we had to pay for the Acela train. So that is mostly true. I can't confirm all the details, but it definitely was decided on the price though.
Okay. Question here. Where are the load dispatchers and power dispatchers located for the New York Penn to Boston portion of the Northeast Corridor?
So the load dispatchers, which maintain it because it's only on the PRR network, had that transmission line. Okay, so the load dispatcher is only one load dispatcher office, and that's in Philadelphia. And they manage from Sunnyside all the way to DC to Harrisburg for the transmission line. That's the very top wire. Okay, the the respective power directors are embedded with each of the train dispatcher or the train movement offices. So we've got some power directors in New York that handle the local, I'm going to call it the catenary voltage on the Hellgate line and in the tunnels in New York, in the New York office. Metroliners got their own power directors in their operations center. And then we've also got a power director office located in Boston, in the Boston movement office. So they're embedded with the train dispatchers. So when there's problems or trouble, they're right there in the same room. There's similar control systems. The computers talk to each other, but so when there's trouble, everybody's sort of there together in the same room to help manage it.
Okay, great. Next question. What's the usual length of wire between counterweights?
It's up to a mile. It could be shorter than that, but it's I don't believe it's anything longer than a mile. So somewhere in the middle, somewhere in that, it's one part of the wire is fixed rigidly, okay, and then everything else is sort of on. If you look at the wires, it's sort of like on a hinge or a bracket, or it can slide through, and it's sort of from the fixed weight, it sort of extends out and goes to the pulley. But the wires really are only about the maximum, I believe, is about a mile in length, because more than that, then it's just too many mechanics and too much force on a wire for it to, plus you don't want to make the wire too long, because if it was too long, it would get really heated up. The counterweights are just going to wind up on the ground then either. So you sort of have to have the right amount based on the wire. There's a formula for it.
Another question, how often is the wire replaced, and what's the oldest wire on the system?
There's a lot of components to wire, okay? And so wire is replaced as it's worn, obviously. So the trolley wire, it really depends on the amount of traffic, okay? So for example, like some of the tracks on the Harrisburg line, get some SEPTA MU cars, they won't get replaced that much. I really don't know exactly what the frequency is, but it really depends on how much it wears versus wire on the High Line going into New York, where all those Jersey Transit trains where we run 400, 500 trains a day on that particular section of track, that wire is going to wear out faster, especially when you got like a 12-car New Jersey Transit MU train with all those extra pantographs going across it. So it really is a variable question. I can say though, there is still some hangars out here. I look at them. I ride the Keystone line to work in the morning. I rode the train, to and from work this morning, and there's still some, I believe, original hangars out there from 1950. They're not even wire. They're like these metal straps. They look like they are so completely different. Insulators, Amtrak did a huge program changing out a lot of insulators and hardware back in the NESIP project days back in the 70s. PRR did some stuff, but they really didn't have the money to really do wholesale stuff. So really, a lot of the components lasted for up to 50 years when Amtrak first started putting money into it after they took over from, PRR and Penn Central. And one of the things you're seeing now, though, is you see, we've been in electrified to Boston for about 23 years now. You do see some components wearing out or some components breaking. We've had some issues up there as we're going through and changing some, different movable hardware components up there too. So it really varies, but some of it can last a long time. Some of it won't last as long. Hopefully that answers the question.
Okay, trying to keep up with
All right.
the comments coming in. I'll get to the Q&A part. I'm just working my way down the comments. Uh, so Kevin does say that he was at Rail Camp this summer and really enjoyed it. Thanks.
All right. Loved having you there. I have a great time every time we meet everybody there every year.
Okay, then let's see. How and when did Metro North ConDOT's rebuild of the New Haven part of the Northeast Corridor electrification come about?
So say it again. How long or
How
how?
and when did Metro
Oh,
North
okay.
ConDOT's
So
rebuild?
so really Metro North, so the New Haven line is divided into two sections, okay? So the section that's in New York State is actually owned by Metro North, and the section once you get past Portchester is actually owned by Connecticut DOT. Now Metro North operates it under contract for Connecticut, but there's two things. So Metro North really started their project. So remember, this is the original 1907. They used to have the triangle catenary up there, and that stuff was old. I remember running engines on that, and that stuff was brutal. That would just beat the pantographs up. It was very rough. It was almost like gas pipe. It was like this really big stuff. So Metro North, really, the first time I remember them starting to do that was about 1990, when Metro North really started doing their catenary replacement. They probably went from 90 to maybe 92, 2 or 3 years to do at least that 10 miles of where Amtrak operates up to Portchester. Then it all kind of stopped for a while. And then ConDOT later on in the 90s started picking it up again, but that took quite a long time to get all that done. I mean, that lasted up until probably about 2014 or 2015. It was a very slow process the way the ConDOT did it. So, I mean, if you're going to say it probably happened over, let's see, 1990, 2010 is 20 years. It's probably over a 25-year span. It took them to do that whole New Haven line, roughly speaking. It could have gone faster. It probably could have gone faster, but it does take time, and there's no way you can do it overnight.
Next question here on the New Haven Boston electrification. How do they power to the middle section of the track on a movable bridge?
So,
Submarine cables or high bridge?
well, so a couple things. The feeder lines go through there's a submarine cable that goes underneath the channel. Okay, they really pass the high voltage through, because what you don't want to have is when the bridge opens, you don't want to interrupt the circuit and like have all the trains on the wrong side of the bridge go dead. Okay, so each of those, there's 5 movable spans between New Haven and Boston, and every single one of those has a submarine cable to pass the voltage around it. Now on the bridge itself, though, there's a section. It's called an MCU, movable catenary unit. So basically, when the bridge is down, these things join up, and there's sort of like a little jumper that goes in there to electrify. So you got a continuous electric circuit across the bridge. Okay. But when there's time to open the bridge, the pieces move out of the way, and then the bridge opens, and that section sort of goes dead in the middle. But so they go through a submarine cable to get to the other side of the water.
Okay, great. And just finishing up the chat part of it. What will be the 5th dimension of railroading?
Maybe that's maglev. I don't know. That's a good question. That's a great question.
Well, that may be a bit meta for us here. So
Yeah. Well,
I'm going to get over to the.
Maybe what we'll do is it'll be an intermodal station for UFOs to come land on the roof. That'll be what it is, right?
Okay. Okay. Moving over to the Q&A now. When was dynamic braking introduced to return power from braking to the catenary? Was it the GG1 or?
It actually goes back before that. No, GG1s could never return power to the catenary. GG1s didn't have a dynamic brake, actually. GG1s couldn't do it. Okay. I want to say, though, I have to think about this. I'm not really sure. Somebody else may be able to correct me if I'm wrong. I do know in the Virginian electrification in the 1930s, on the Virginian could put their train with the colos coming down the hill and put it into regen mode and would supply the power. They could run the empty train up the hill. So that was available in the 30s. Okay. Like that. The New Haven did not have that. I don't know if the Great Northern had it. I'm not sure about the N&W had it. So my personal knowledge, I know the Virginian could do it in the 30s. Somebody else may have some better information than me, but that's as far back as I can go with it. The PRR actually did not.
Okay. What about the future? Battery electric or expansion of catenary?
Both. Okay, both. So right now, folks see Tesla and all the stuff that goes on in the Tesla. See, how far can my car go? Charging stations. You need this whole network of stuff. Amtrak is exploring some battery electric trains right now as part of the new Aero project. Like even for the Empire trains, to be able to run on diesel, and then use the battery electric to kind of go through the tunnel there, perhaps. So battery electric, I think, is can be viable to fill in those short distances where you don't need a lot of horsepower, but the amount of weight of batteries you need to be able to create that amount of energy, or the joule is all measured in joules, is so tremendous. It's not really efficient over a big long distance. So if you're going to run really fast and you use up a lot of energy, you have a lot of trains, electrification is the way to go. If you have shorter stuff, you want to do something simpler to get it started. You see Henry Posner's pop-up metro out there. It's all batteries. Battery works fine for that too. So it really depends on the need and what you're trying to do. They both can serve a good purpose depending on what the application is, frankly.
Okay, I think we already answered what's the oldest wire on the system.
Yep.
1915
1915 Paoli. 1907 New Haven, if you want to count the New Haven.
Okay. Oh, a couple people did put in the comments that the Milwaukee Road had regeneration.
Yeah, okay, yep, yes they did. Yes, they did, actually. You're right.
Okay.
I don't know if they beat the Virginia or not. I have to look at the year when they did. They actually may have yeah, the Milwaukee, because they were what, 1918 they electrified, I think. They actually may be the first one. Yeah, you're right.
Okay. Specific question about a picture. The Metroliner picture going into revenue service in January of 1969.
Yep.
And the question is probably, yep, that one. Are those cars still running around with modifications, or are they?
So none of them are running around in the current configuration. Okay.
Well, I don't think that's the question. Are they running around in any configuration?
So the only car number I can see here is the 864, and that's the food car. And I don't think that's it. I think the 863 was our 9800. I forget which one. So we only have one food car that's left running is the 9800 Commerce car right now, and I don't remember the number offhand.
Okay.
I can find Amtrak by the numbers right behind me here. I could probably pull it down. But
anyway, don't worry about it.
Yeah, all right. But so a couple of these coaches you see back here could be running today as cab cars. There's about 15 of them or so that are still active in the fleet right now.
It actually, since you've got that picture up, I'm noticing between the second car and the third car, and the fourth car and the fifth car.
Yep.
Are those like cabs that are end to end, or?
Yes. Yeah. So these are back to back. So if you look here, so there's one pantograph up, all right, and they're all coupled back to back. So the Metroliners, to cut down on the number of pantographs on the wire, to reduce your wire wear, but also to create, because every time the pantograph goes over the wire, it creates a wave effect in the wire. So this pantograph on this car is down. There's actually a bus jumper. When they would switch these in the shop, they'd hook up the two pantographs as a jumper going across. They hook them up electrically, so you only had to have one pan up for every two cars. So you see 3 pans and 6 cars. Yeah, that's what it is. So this is the front of this car. There's the front, and you have 2 fronts coupled together here, 2 backs coupled together here, 2 fronts, and 2 backs is actually how that train is made up.
So basically, every one of the Metroliners was basically the original one was basically a 2-car set with a cab at each end.
Well, actually, they were actually single car sets, so you could actually run odd number. You just want to make sure there's cabs at the outside ends. Like when you looked at them in Keystone service, you could have a cab forward, a back, and then the cab rear that way. You could actually run them in less sets, but it was just this train happens to be an even number of cars.
Okay, great. Okay, we got that one out of the way. Let's see. So I think a couple people asked this one. What keeps the points where the pantograph and catenary contact from melting from friction at such high speeds?
Well, on the top of the pantograph is a special wear strip. I don't know if I got one. If I was in my office, I could pull one down for you here.
That's okay.
There's actually a carbon strip. It's made out of carbon, so it's made to slide. I mean, ultimately it will wear out, but it's designed to take the power, it's designed to take the electricity, and it slides along without falling apart or falling away. One of the dangers though is sometimes they will break. And so what the modern trains all have is they've got actually a little air channel in it. So if a piece of wood to break away, the engineer says, "Oh, broken pantograph alarm," and automatically drops it right away before you actually screw up the wire. Like if a piece of it breaks away at the wrong time. But yeah, there's things called carbon strips in the in rides, and it sort of glides along. It's sort of like this sort of slick surface, but it actually is a very good conductor of electricity. And you know, it's not metal; it's carbon.
Okay, I actually when the Acelas first went into service, we uh, did a little outing and got a tour of the Acela shop up here
Okay.
in Boston. And my recollection was at that time that the contact strip on the pantographs were being replaced at about every round trip. They were really wearing out very quickly.
That seems a lot, but I mean, they do have to get replaced though. But I'd have to find out about how that seems to be a little bit like maybe at first they were, but I think that's much better now. We're not doing that anymore.
Okay, moving down the line here. That's live. I guess is a sort of a lead in the next month's program. Is there something equivalent to Sperry rail systems for rolling along and checking the mechanical characteristics of the catenary system?
Well, not quite as good. Not quite as good yet. That technology's not there yet. But one of the new things Amtrak has, and you'll see it sometimes for the folks, if you ever see like when the inspection cars come up, usually they go back up on 172 and back on 171. There's a car, it's a 10,005, and it's actually one of these old cars. I forget, it was an old coach. It still got the pantograph down on it. And we have this array of about 24 or 30 lasers on the roof of it we can look at the wire height, we can look at joints, we can see if there's like the spots in it. And it does, we do it actually at track speed. It's beautiful array of lasers. It's really high tech stuff. And we look at it. So it's not tested the metallurgy, it's not reaching deep into the wire like Sperry reaches into the rail, but we're looking for all sorts of different things. It can identify all sorts of things or broken components. It's really fascinating what it does. So it doesn't quite do it, but then again, if I have a broken wire, I don't have the same result as if I had a broken rail. Okay, so I may rip some wire down, I may bang up a pantograph and delay a train, but I'm not causing a catastrophic accident. There's a difference why we don't actually have to inspect the wire with the same level of rigor that you do have to inspect the rail.
Okay. How many different voltages or frequencies are in use between Washington and Boston? And are there any plans for standardization?
So there are three different frequencies. All right. So the south end of the Northeast Corridor, New York from Sunnyside essentially to Washington D.C. is 12,000 volts, 25 cycles. Okay. The Hellgate line and the Metro North line is 12,500 volts at 60 cycles. So they don't have to have those converter stages. They just plug right in the power grid. But the difference is though, because of the way the power is, you have to have all those extra phase breaks in there. So that's why the lights sometimes go on and off because you're running over different electrical sections. It's not all phased together. And then from New Haven to Boston, the modern standard, where it's really anything gets installed at these days, is really 25,000 volts at 60 cycles. So it's much higher voltage, much less substations, less metal you need in your catenary system. And ultimately, at one point in time, you know, back in the 70s, it would the whole 25 cycle was supposed to get upgraded. The 60 cycle here go to 25 kV on the south end. It's a hugely expensive project. And although we'd love to do it someday, right now the funding, we've got a lot of other stuff to spend the money on first to replace bridges, tunnels, tracks, mud out of the track. You know, the money's going to go there first because those are more pressing needs than converting the voltage. So will happen someday in the future. It would be good. It's nice as other components wear out. But right now, the money is better spent doing some other stuff, which is which is happening.
Okay. Is yes or no answers, please, here, Chris. It's getting late. Is Metro North willing to increase speeds on the New Haven line to 160 miles per hour? Would Amtrak like to take control of Metro North's portion so speeds could be increased?
That's a lot. So, real simply, the railroad is too old to go 160 mile an hour on it. But Metro North is willing to increase speeds, but you'll never go 160.
Okay. Oh, this is just getting detailed. If the Bridgeport, Connecticut to Ronkonkoma Long Island Tunnel gets built, approximately 25 to 30 miles, what will be the unique electrification requirements?
Good question. My guess is if you're going to build something new, you'd probably build it at the 25 cycle, 25,000 60 cycle would probably be the best way to go. You don't get snow. It's not affected by snow like the third rail is affected by snow. It's modern voltage, less substations, less metal for all those reasons I just mentioned. Build it to the newest standard.
Okay. Let's see. I guess the question about the oldest piece of wire is what's the oldest piece of wire? And I presume they mean the trolley wire that's still in service.
I mean, I don't know. I wouldn't even have that record.
Okay.
I mean, is there something there from 1915? Perhaps. Highly unlikely. Things have gotten changed over the years, but there's definitely still poles all out there from 1915. I see them every day.
All right, let's see. Cost difference between third rail electrification and catenary?
You probably have to go Google that. Once again, for all the things I mentioned, though, more material, more substations, more maintenance, all that sort of thing. Plus, you get problems with the third rail. Animals get into it. Snow gets into it. It's got all sorts of other issues there too, which I sort of mentioned in one of those earlier slides. So I don't have the number. It really depends on the installation and the trains. It's very variable.
Okay. So jumping over to the chat. Alan says the TGV has overhead wires that zigzag to minimize wear on the pantographs. Is this true on the Northeast corridor?
Where we have installed the constant tension, yes. Where the constant tension is. Where the PRR wire is, no. It's all actually very nice and it's pretty straight. You see, I mean, it's a little bit of zigzag there, but that doesn't count. I mean, this is about a 2-mile shot. Some of this gentleman here, Mitch Goldman, thank you if you're on here. Make sure you get the copyright on here. It's pretty straight here, but when you do constant tension, that is a standard to zigzag it across, and that's the way all that new stuff is built.
Okay. Let's see. I think we just kind of answered that one. Siemens Electric locomotives, the current preferred supplier. You can duck that one if you want.
Well, no, I mean we've got that's an Alstom train, right? We've got and we've got Siemens train, so we've got both. I mean, is that preferred? Whatever's got the best deal for the best job at the best time.
Okay, and save this one for last. So
okay,
don't let anybody put anything else on. What's the inside scoop on when the new Acela train sets will actually launch in revenue service?
Well, we're working on
20. We won't tell anyone.
Well, no, I told you guys already. I told you already. We're working on 2024 launch. I don't have the exact date though. We're still going through some testing. You'll see some more testing coming up with it soon here as we work through some stuff. But we'll have to. So at some point in time, that's going to be a whole long story for a different presentation. Okay. How's that?
Well, we plan to have a presentation about the new Acelas when they around the time they go into service.
Let me know.
We'll have you back then to talk about that.
Yep.
Okay. Well, at this point, I think we've pretty much exhausted everything. So, Chris, I think we'll wrap up the formal program right now. So I just want to thank everybody who stuck around. We've still got over 80 people hanging around for this. And Chris, I want to thank you for a fabulous presentation. I think we all learned quite a bit about electrification and technical aspects of it. So just a wonderful job, and we look forward to having you back for another presentation that sometime in the future. So